let's move on to the next speaker. Professor Naidoo, I think it's your time now. Lebu, are you sharing Prof's presentation?
Morning.
Morning, Professor.
How are you doing?
I'm good. How are you?
All right. I have to share my presentation on PowerPoint.
Okay.
I'm going to upload it now, if I can get to it.
All right.
There it is.
All right.
Is it there?
Yeah, it's coming. Yeah, it's there.
All right. Super. Let me stay to
slideshow.
I'm going to do that shortly. Okay, there we go. I simply get rid of this tab out of the way. All right. I don't know if, can I start or you want to say something else?
No, you can start.
All right. All right. Thank you, everybody, for the opportunity to present some of the work we do as part of the Center of Excellence in Strong Materials, of which I am a member, and based at Wits University, as you can see. Information is just some background knowledge on work that we've done in the past in regards to the transformation of diamond. And you may find it strange to understand why do we want to take this beautiful material and transform it. Well, the beauty of diamond is not in its beauty, it's in its imperfections and its applications for physics. So I'll just give you a brief overview of how I'll take you through this talk. Just a bit of an introduction into diamond, specifically carbon and what's so special about carbon, and then just look at what we mean by ion beam modification and tell very, very briefly about different techniques we use to understand the transformation that occurs and what we want to use it for in terms of the applications and conclusions. So that's just a brief overview of what I plan to say. So carbon is definitely special. It's a group 4 element, and we're very familiar with these group 4 elements because silicon is the major player in the semiconductor industry in terms of its material applications, and it's almost like nature provided us one of the perfect candidates of materials that can be easily transformed in a sense that you can change its electronic properties. So this is the group 4 semiconductor material that's dominant in terms of semiconductor applications in our technology today. Diamond forms, or carbon also forms the diamond structure, like silicon does and everything in the group 4 element. But what's special about carbon is that it's a self-assembly easily happens that it wants to always revert to sp2 carbon. And that's an important observation to understand, is that in essence, that because it wants to do this transformation to sp2 carbon, we find that diamond in the sp3 form, which is the diamond structure, the cubic form of diamond, occurs under special assembly conditions. But under normal circumstances, diamond, or rather carbon, wants to relax to this sp2 form of carbon. And this is why you can easily see this transformation leads, or this self-assembly leads to some important materials that we've become familiar with in terms of what's in the literature and scientific literature for physicists especially, and many other people for the matter, is graphene and carbon nanotubes. So this is one of the few elements in that group 4 that can do the self-assembly and support its sp2 structures in the form of a sheet, which is a graphene or honeycomb structure sheet, and the carbon, which is a rolled graphene sheet, if you want to think of it that way, and these fullerenes or the buckyballs. Silicon can do it, but it needs a support structure around it or inside of it. So that's not so easily obvious in silicon, which tends to rather form more easily the sp3 structure, which is the diamond structure. So just to give you a background that this material, in terms of carbon, it's the way it can form different types of bonds, which is sp2 and sp3, is really unique in terms of its group 4 status. So one of the things that's hopefully apparent to people in this talk, or maybe it's apparent to some others, which is not your field of expertise. I understand that. Just to tell you that to be able to generate diamond from, let's say, coal or graphite or some other form other than diamond is possible by two processes. So the one process that we are very familiar with is called the high pressure, high temperature process, which generates diamonds. We're using this process, which is much lower than we find in nature. Nature does the same process in converting carbon to diamond. It does it at high pressure and high temperature, deep down in the depths of the earth. That's where most diamonds have been formed, which are what we call natural diamonds. Then we have this class of diamonds, which I call, they call it synthetic diamond, but it's a very misleading name because synthetic suggests almost that it's not diamond, but in fact it is diamond, and it's just what I call man-made or laboratory-grown diamonds under similar conditions of high temperature, high pressure, much lower in temperature because we use a metal solvent catalyst in order to generate this growth. But important to understand is that you can take the sp2 form of carbon and convert it to the sp3 form in this process. Very, very exciting. The ventures nowadays is what they call chemical vapor deposition. So this allows diamond to be generated in the form of thin, flat, almost like wafer-like structures, not in the same range of size as a silicon wafer, but very similar in its approach to trying to generate diamond using what is called a low pressure process. And it's a gaseous phase of hydrogen and hydrocarbons, which is usually methane, in a reactor chamber, and there's different types of reactor chambers, microwave CVD or hot filament CVD, plasma CVD. There's a range of techniques that uses the gaseous phase to precipitate out onto a seeded substrate the sp3 form of carbon. The important aspect of this process is the hydrogen, which etches away the sp2 carbon and leaves predominantly behind the sp3 carbon, which allows diamond to grow and high quality diamond to grow, so much so that it's even better than what you would find in nature. So a very important process and development in recent 2-3 decades. Has been a fast moving industry, and lots of people are now growing single crystal diamond using chemical vapor deposition for applications, which I want to talk to very, very shortly. But before I get there, what I want to just very briefly discuss with you is one of the things that we are interested in is taking this diamond structure and breaking it down. And breaking it down using ionizing radiation. Misleading word ionizing here, it doesn't mean it's gamma rays or X-rays or anything of that nature. It's radiation, and the word radiation is used for fast-moving particles which are generated in an accelerator. An accelerator-based physics is a long topic to talk about, but let's just say you can produce any ion, which is basically a charged particle, and you can accelerate it, and using electric fields and magnetic fields, you can focus it and you can effectively introduce it into a material. This process of introducing foreign atoms into a structure is called doping in the semiconductor industry. It causes a transformation of a material in terms of changing electronic and optical properties primarily. And it's a big industry in terms of the semiconductor industry in this process of using ion implantation. And I think the next speaker is going to tell you more or less something else about our ion implantation can also transform a lattice structure from hexagonal to cubic structures. But for me, I'm interested in completely destroying the structure. And the way the damage that occurs and precipitates is an important process that we want to try and understand. Different types of models that describe how radiation damage accumulates in diamond. I'm very much a supporter of the accumulation of point effects by a ballistic model. The displacement spike is also commonly touted as a possible way of describing how radiation damage precipitates in a material like diamond. It's very different from the other group 4 elements, but I don't have time to talk too much about what happens in those systems. But in diamond, definitely we have this destruction of the structure, and the more and more atoms you force into it, and this is a non-thermodynamic process, you destroy more and more bonds. And the more bonds you destroy, the more easily it collapses to the sp2 form. And that's a very interesting idea that we can use, because we can create, as you will see, structures that are different to diamond inside of diamond. So I just want to show you quickly what happens in some kind of process where ions are introduced. They're introduced with an accelerator, usually quite high energies. When I say high, it's much higher than 2 or 3 keV. It's of the orders of hundreds of keV, but not in my case in the orders of MeV. Of course you can. What happens is the ions traverse through the solid, and then they eventually come to stop inside the solid. And at the end of range, as it's called, you get a lot of ballistic collisions that happen, and they knock off other atoms out of their atomic positions. And this is how you effectively introduce foreign atoms by a non-thermodynamic process. Initially, the atom doesn't slow down, or it is slowed down, but not substantially, by a process called electronic stopping. And eventually, when it comes to rest, it comes to rest in a process called nuclear stopping. So that's basically just a quick overview of what you can imagine to be a simulated idea of how atoms are, or ions are introduced into a material. Of course, they cause damage, and the damage is simulated damage, which we refer to as the vacancies that is produced. And vacancies are where atoms are knocked out of their lattice positions by the incoming atoms. As they come to stop, they knock off other atoms in the lattice, and they cause this vacancy accumulation. This is a simulated vacuum thing, which is called in a program called SRIM or TRIM, this transport of ions and matter, and it's basically telling you how much damage you are generating in terms of a simulation. Not so much how much, but rather where is the damage, and the atoms are going to come to rest. That's the more important parameter you can extract out of this kind of simulation. And we have also extracted some other theoretical value, which is called the damage. And we'll find that at certain levels of the simulated damage, we find that the diamond structure doesn't recover after you've introduced a certain number of atoms. And we call it the critical threshold of damage. So let me just show you very, very quickly. What happens then is that if you choose, for example, in this example that I'm showing here, an implantation temperature, which is room temperature and 150 keV energy. In this case, we use carbon ions for this presentation that I'm using here. And I'm showing you a bright field. I apologize, selected area diffraction on the right-hand side. And of course, on this side is a TEM micrograph or transmission electron micrograph of how we can view what is taking place after the ions have basically destroyed the diamond structure. What you find is that where the ions come to rest, you have this amorphous or no correlation on crystal structure anymore. This is the diamond substrate that you start with, that you can see diffraction contrast, which tells you something about the crystal structure is very much intact. In the region B, where most of the damage has occurred, you find that you're starting to form this graphitic arcs, which tells you that there's an sp2 form of carbon that is starting to accumulate in this volume. And where the ions don't interact much with the lattice, the electronic stopping region, you find that the diamond lattice still remains much intact. And it's only where the atoms or ions come to rest do you have this idea of this amorphous carbon. Now, if I introduce a lot of knock-on collisions that creates a lot of damage in this amorphous region, when you anneal the diamond, which means when you increase the temperature afterwards and you want to recover that lattice structure, you won't. This little region will collapse to a graphitic form of carbon. And this is what I'm interested in this actual graphitic form of carbon. So I'm rushing a bit, I know, but just to show you again, TEM or electron scattering, as it's called, is a very useful probe. And this is part of my talk, is to advise you that you can use electron microscopy as a very powerful tool to analyze what radiation damage occurs and where it occurs in your crystal structure. In this case, it's diamond. So I'm sorry, I don't have a lot of time to take you through the details of this, but if I just look at the center micrograph, what you're trying to demonstrate here.
You have a minute there, Prof.
I have a minute left, my word.
Yeah.
Okay, so this is just basically an overview of how you can introduce the radiation damage. Just to I'll just take you through you can get core loss and low loss yields information that tells you more about the type of diamond you have. A very, very important thing is you can use optical scattering, Raman, which is a way of understanding what defects you create, point defects and accumulated defects. These very, very narrow structures are from point defects. This is the perfect diamond crystal. So photons is also a useful tool in trying to understand what kind of damage you created. So another useful way of, just give me a little over a minute, is using optical techniques. It's called surface Brillouin scattering, where we can actually understand the elastic properties of this layer that you've created, which is in the implanted region. And you understand you can now alter the elastic properties of a buried layer inside the diamond structure. So this is what we've done. And the reason why we've done it is that we want to understand a lot of, in terms of the conclusion now, how we can use this to create mechanical systems with different elastic properties inside the diamond. Also, interestingly enough, how can we use this to create electron phonon coupling in the system, which will produce a Seebeck effect. And we want to understand if can we use the system that we create to generate thermoelectricity. So that's the next step of this project in terms of why we're doing what we're doing, to destroy the diamond structure, as it were, and understand the electronic properties of this buried layer. So a lot of the work is got to do with my PhD graduates, which have graduated in the past, and the current students who are working on the system. Colleagues and collaborators, like to thank them all, and especially the DST-NRF Center of Excellence in Strong Material for supporting my research over these years. And thank you very much for listening.
Thank you very much, Professor Naidoo. The floor is yours, Professor Cornish.